All right, so we're just going to finish up number 32 because we haven't done a limit comparison test, I think, in this section yet. So we're going to try doing that. So basically what we want to write out is what is our problem series. So we're going to let a sub n equal e to the 1 over n squared. And just notationally, it'll be easier if we write out what a sub n and b sub n are. B sub n is going to be 1 over n squared, because that allows us to then write what is the limit as n approaches infinity of a sub n over b sub n. So that's going to equal the limit as n approaches infinity. So we'll first just put a sub n as it is here, e to the 1 over n squared. And then instead of doing divided by b sub n, we'll go times 1 over b sub n. So b sub n is 1 over n squared. We'll go times n squared over 1. And then that's pretty nice because then I get limit as n approaches infinity. The n squareds cancel. I just have e to the 1 over n. Now you can take a separate step and say e to the x is a continuous function, so I can bring the limit as n approaches infinity inside and have e to the limit as n approaches infinity of 1 over n, then show that limit as n approaches infinity is 0, so I have e to the 0, which is 1. But probably it's good enough for us to say that since this is approaching 0, I just have e to the 0, which is 1. So the only important thing I like about that, number one, is that it's between 0 and infinity. What's nice about the limit comparison test is you have a huge target to hit. If I get anything between 0 and infinity, I'm happy. That's a pretty big range. So we got that and we're happy. So now we just have to make our conclusion. I do have to state why my comparison series converges. Sum from n equals 1 to infinity of 1 over n squared. This book sort of, my first complaint about it is they sort of overuse this p series with p equals 2. They could have used p equals 3 just once, or p equals 60 or something. That's anything greater than 1. You could use p equals 1.5, but no, it's always n squared. But you could have anything on the EP exam. So converges because it's a p series with p greater than 1. So we have to say that, and then we get to say that the sum from n equals 1 to infinity of e to the 1 over n squared converges. We can't just say the series converges this time because we have two different series that we're talking about. So we have to be specific about which series. This is our problem series, and it converges by the limit comparison test. All right, so what are the key features of the justification that I need to prove that this series converges? I need the calculation of the limit. I need to show that that limit fell within the value specified by the test. I need to say why the comparison series converges or diverges. It could have been a divergent sequence. And then I need to state that my problem series converges, and state my conclusion, and I need to cite the test, limit comparison test. Remember, if you do limit comparison test and you get a value between 0 and infinity and your comparison series diverges, then your conclusion is going to be that your series diverges, because the test concludes that the comparison series and the problem series either both converge or both diverge. So that's number 32. So good luck doing the rest of the problems in this section. Remember that what I'm assigning is section 9.7. This is your homework on this. Section 9.7, which is page 710. We're doing number 6 through 33, the multiples of 3. Multiples of 3. All right, enjoy.